Hi, can you hear me? Am I audible, visible? Mr. Kalimoto, can you hear me? Can you join with your mic, and we can talk a bit about your question? You can also send me a chat message if you are not able to connect to the audio.
Hello.
Yeah, hi.
Professor.
Hi, nice to meet you.
Yes, Professor. Thank you so much, Professor.
You're welcome. You're welcome. My pleasure. So, where are you from?
I am working as an assistant professor in Perundalaivar Kamaraj College, Puducherry.
Oh, okay.
This is my fourth NPTEL course, Professor.
Okay. And you're teaching mathematics.
So mathematics for undergraduate, Professor.
For undergraduate, yeah. And what kind of mathematics courses do you have? Like BSc, MSc, or
BSc Mathematics and BCom BCA.
BCom BCA. I see. Okay.
Yes.
Can you hear me? Okay. Is it clear?
There is a slight audio switching.
Oh, I see. Not sure how to fix this.
Okay, Professor, no problem. I can adjust.
But if you can understand, then you can go on.
Yes, Professor.
Okay, good. Okay, yeah. So this course was meant for basically for undergraduate students in mathematics for BSc onwards.
Yes,
and yeah, so points and topology is something very basic that anyone studying mathematics has to learn, and I mean it's everywhere in mathematics almost.
Yes,
so,
yes.
So it's something very foundational, and one has to understand. It's also a first step into the abstract world of mathematics.
Yes, Professor.
So it's something that it's my favorite topic to teach. One of my favorite topics.
Okay, Professor, it's pleasure.
Yeah, so I think I read your question. I understood what you meant about the dictionary order on the ordered square, right? So you wanted to have examples of open and closed sets. Okay.
Yes, Professor.
Yeah. So let me share my screen, and I'll just explain these sets. Okay. Can you see my screen?
Yes, sir. Yes, Professor.
Yeah.
Yes.
Okay. So just let me. Yeah. So for the ordered square, right? For the ordered square, which we denoted at something like I0 square.
I02.
Yeah. So it's just as a set, it's just a unit square in R2, right? So this is 0, 0, 0, 1,
yes.
1, 0, 1, 1, and
1, 1, 1.
right? So this is just the unit square as a set. Okay? As a set,
Yes.
as a set is just 0, 1 cross 0, 1, right? The dictionary order. So we first thing we want to do is to put a topology on it before we speak about the open sets and closed sets, etc. We want to put a particular topology, which will be the order topology, as we have seen. Right?
Yes.
So the dictionary order. Let me recall what it is. The dictionary order is defined as follows. So let's take 2 points. Let's take this point A and another point B. Okay, so,
Okay.
so A, B, A1, A2, B, B1, B2. Right?
B2.
And the usual dictionary order is defined as follows. So we write A is less than B, right?
Yes.
If and only if.
If and only.
A1 is less than B1. So the first coordinate, the x coordinate, is strictly less than
B1.
B1, or A1 equal to B1.
Equal. Then A2 less than B2.
Exactly. So this is the dictionary order. So with this order, this I0 square becomes a linear continuum, right? So this is the theorem.
Yes. Okay.
I think I proved it in the lectures that
yes, Prof. Yes, Prof.
Yeah, is a linear.
It's a linear continuum.
Continuum, right? And so with the now we can put the order topology. So put the order topology on I0 square. Okay. And with this order topology, so with this topology, so the first thing to know is the properties of this topology. So what are the basic properties? The first is that it is Hausdorff.
Hausdorff.
Right. So let's see what is the so what are the basic sets for the order topology, right? So the basic sets, open sets for the order topology, they are defined as follows. So they are now pairs of points. So A comma B. Okay. So this is the set of all points x comma y in I2. So in 0, 1 cross 0, 1.
Yes.
Such that you have A1, A2 is less than x comma y, and x comma y is less than B1 comma B2. Right?
Yes, Prof. Yes, Prof.
So this is the open neighborhood, basic neighborhood. So what does it look like? So let's draw a picture, leave a picture. Oops, sorry. Okay, so now you have 2 points, right? This is A1, A2, and suppose you have another point B1, B2,
B1, B2,
right? So first of all, let's see if you have another point, say here in the same vertical line segment. So this is x. This is the vertical line, x equal to A1. Right?
A1.
So
yes.
Vertical line.
Yes.
So if you have another point, let's call it x comma y. If this is here,
okay,
and then you see that the A1 equal to x. So
x.
Right, but so then we have to compare the y coordinates, and in this case, A2 is less than y.
Less than
so
y.
This means that x comma y is rather A1 comma A2 is less than x comma y, right? So A1 comma A2 is less than x comma y in this case. So so the open set that we have starts from this. Okay, so it starts from this, but does not include this point, and it covers all the points in this upper half of this vertical line, right?
Okay. Okay.
On the other hand, if you have any point here in the vertical line segment, this is x equal to B1 now,
B1.
right? And your point x comma y is somewhere here, right?
Okay.
So then x equal to B1 here, and then again we can compare the y coordinates, and we find that y is
less than B2.
Right. So then we find that x comma y is less than B1 comma B2.
B2.
Right? So now we have all this part of as well. So the open set ends here, starts here, ends here. So what about the middle point?
Okay.
So if you have any middle point somewhere here,
okay.
So I'm using the same x comma y notation for all three, but they are different points.
For any points.
Yeah,
in
for
between.
any point, in between. Yeah.
Okay.
So in this case, A1 is less than x. Okay. So A1 is less than x.
It's less than x.
And x is less than B1 as well. Because it lies in the open interval from A1 to A1 to this. Yeah. So in this open set from A1 to not A2, sorry, A1 to B1.
A1 to B1.
Yeah. So this x lies in the open interval A1 to B1. So A1 is less than x and x is less than B1, right?
Okay.
And this holds for any point in this whole vertical line. So including these 2 points, including the point 0 and 1, right? So this means that the open neighborhood AB, where A is this point and B is this point, it consists of the upper line here. So I'll just put this in the green shades, this part.
And in between A1 and B1?
And all vertical lines in between.
Yes.
Okay. So everything in between. So not this part, but it just touches this.
Between the 2 lines.
Right. So all of this. So this is a usual basic open neighborhood in the order topology, right? So how is this Hausdorff? So maybe if we prove it's Hausdorff, it will become clearer how things work, right? So let's try to see how it is Hausdorff. So Hausdorff means
distinct point can be separated by distinct open sets.
Exactly. So let me draw another picture. So again, if you have distinct points, say A1, A2, and let's say B1, B2 is here on the same vertical line. Okay, so you have A1 equal to B1 in this case, A2, right? So what are the so if it's on the same vertical line, then the order rather the order relation on this vertical line is the same as the order relation with respect to the real numbers, right? Because you are fixing the first coordinate, and the order relation just considers the second coordinate. Right? So it's the same as the usual order relation on R.
Real line. Okay.
Oh, yeah, exactly. So now, because R is Hausdorff, you can say immediately that if you have two such points, then you can find open sets. Okay? So these open sets will be of this form. So something like this. And something like this. So this is B, and this is
U.
Right? So this will be there will always be disjoint open sets separating the 2 points, right?
Yes.
If you have any other point, say B1, B2 here, then it's even easier, right? Then you can have any such U with the same U as this one. You can have a V which is in the entire thing even here. Even
yes, vertical line. We can take the vertical line.
Yes, this will work. Right? So this is the Hausdorff property.
Okay.
For the ordered square. About closed sets. Closed sets is a bit more interesting. So let me draw another, or maybe I can copy it. Yeah, so for closed sets, let me just remove the parts that we have seen. So one of the examples of an interesting closed set here is this problem set. So we have this horizontal line now. Okay, so rather than considering vertical lines, you consider the horizontal lines. And so this point is A1, A2, and this point is B1, B2. Okay, and this line segment contains its endpoints. Okay, so this line segment L is nothing but the set of all points x comma y, such that A1 less than or equal to x less than or equal to B1, and y is equal to A2 is equal to B2. Right. So this is the line. Now I claim that this line is closed. So why is this closed? So to prove that it is closed, we can use the very definition of a closed set, which is that its complement is should be open, right? So if we can prove that given any point, let's call this CD, we can find a basic neighborhood which does not intersect this this closed set. Right? Then you have shown that the complement of L in I0 square is open, and that implies that L is closed. So you can actually visually you can see it quite easily, right? So if you have such a point CD, then you can just take some vertical line here, okay, and then take some small open neighborhood in the order topology. Say this is U, okay, and you can make U small enough so that it does not intersect L at all, right? This is possible. Do you agree?
Yes, Professor.
Yeah. So, yeah, any other questions? Yeah. So we have that. So for such a point, we can always find an open neighborhood which does not intersect L, which shows that. So what we are proving here is that L complement is open, meaning that if given a point CD in L complement, there exists an open neighborhood U of CD such that U, first of all, CD is contained in U. CD is contained in U, and U is contained in L complement. This is what we want, and this is what we are trying to show visually. Okay? So this proves that this implies that L complement is open, and this implies this is the equivalent thing to say is that L is closed. Okay. So yeah, so L is closed. So of course you can do this for other points as well, right? So you can take a point here, you can take a point here. So you can have these points anywhere you like, and depending on where you are, you can also have a point here. And depending on where you are, you can take either the whole vertical line segment. In this case, you can also take the whole vertical line segment. You can take it smaller, bigger, it doesn't matter for this case. You can take the whole thing here. For this point, you have to take something smaller. So all these open neighborhoods will. So the open neighborhood itself will change depending on the point, right? But so this U depends on the point that you have chosen. But for each given point, there exists such a U for which this condition holds. Right? So this is an example of a closed set. What about? By the way, what is the interior of this set? So let's while we are discussing this, let's see if we can if we can find the interior of this set L. So what is the question? What is interior of L? Any guesses? So what is the interior of the set? Interior of set A is the largest open set contained inside it. So it is the union of all sets U, for which U is a subset of A. U is a subset of A, and U is open. Right? So this is the largest open set. So what kind of open sets can be contained inside L? Any guesses from listeners? No? So if you take a point, let's have a point here. And you take an open set. So suppose that there exists a empty open set U inside L. Okay? So this means that some open set of this form lies inside L. Is this possible? Because
no, Professor.
This is not possible, right? So you cannot have any non-empty open set inside L. So this means that interior of L is empty. This is what we discussed in I think week 9. So when we were discussing the Bayer spaces, we discussed what is the interior, and we formulated the Bayer category theorem in terms of closed sets with empty interior, right? So this is an example of a closed set with empty interior. Another interesting question for this particular set is whether L is compact. What do you think? So by the way, once we are moving to compactness, so let me just mention here, compactness is that I0 square is a compact Hausdorff space. Right? Why is it a compact Hausdorff space? We have already seen that it is Hausdorff. Why is it compact?
This is closed and bounded. Can we
closed and bounded in the standard topology, but in the dictionary topology, so there is a difference. When you are talking about closed and bounded, you always have a metric space underneath, right? You can only talk about bounded sets in a metric space. On the other hand, this I0 square is a subset of R2, sure, but it is not given the metric structure. So compactness, when you are talking about compactness, you always have to specify which topology you're talking about. So we are not taking the standard topology on R2, right? So of course, in the standard topology on R2, this unit square is compact because it's closed and bounded. But so this is what is this theorem called? This is the Heine-Borel theorem, right? So Heine-Borel. So Heine-Borel theorem says that any closed and bounded set in a linear continuum is compact, right? So in this case, bounded is not with respect to a metric, but bounded is with respect to the order relation that we have, right? So this I0 square has a least element or an infimum and a largest element, a supremum. So what is the infimum? So infimum is just this point 0, 0.
0, 0.
Right? So 0, 0 is less than or equal to xy for all xy in I0 square. Right? Similarly, the 0.11 is the supremum. So xy is less than or equal to 1, or all xy in I0 square, right? So these are the smallest and largest elements, least element, largest element. And with this definition of boundedness, so I'm just trying to differentiate between boundedness in a metric space and boundedness in a set with an order relation. So here we are using the Heine-Borel theorem for boundedness in a set with an order relation, and in fact it's a linear continuum, right? So the Heine-Borel theorem says that any closed and bounded set in a linear continuum is compact. Of course, I0 square is closed, right? Because the complement is the empty set, this is open. So I0 square is closed, and it is bounded because you have I0 square is bounded since we have 0, 0 less than or equal to xy less than or equal to 1, 1. So the same thing cannot be said for the Euclidean plane. So R2 in the dictionary order. So R2 in the dictionary order is not a compact space because it's not bounded. There is no least element, there is no largest element. So it's not bounded. But now that we have the Heine-Borel theorem, we get immediately that I0 square is a compact space. And we have already seen its Hausdorff. So in fact, this is a compact Hausdorff space. And if you have already seen the weekend lectures, then you will know that this is in fact a normal space. Right? So given any two closed sets, you will have closed disjoint sets. You will have open neighborhoods, right? Open neighborhoods separating them, right? So this is in fact a normal space as well. And of course, this implies that it's a regular space, right? What about bare property? Is it the bare space? The ordered square? Bare property? Is it a bare space? So we have this bare category theorem, right? So the bare category theorem says that compact Hausdorff spaces and complete metric spaces are bare, right? Are bare spaces. So from the bare category theorem, it is immediate that I0 square is a bare space. So we just start with the most basic definitions, and we build upon these things in relation to our platform of basic things, and we try to look at it at different angles. So we are looking at the ordered square in terms of its compactness, in terms of its linear continuum property, in terms of Hausdorff property, in terms of regular, normal property, bare property. All these are different properties of the same space. And so there are various applications, as we have seen, that if you have a bare space, any dense G delta set in a bare space is uncountable, for example. So I0 square is uncountable. So this is just another immediate result from the theory of bare spaces, right? So I0 square is uncountable. And in fact, the bare category theorem is extremely useful in analysis. And when you do functional analysis, the bare category theorem is applied a lot. So it's very, very useful. Okay, now coming back to the example that we had of the set L, whether the set L is compact. I'm sorry, there is some construction going on. Sorry about the noise. So whether L is compact. L is compact. L is compact. Or not. So what do you think? Whether L is compact or not? So of course, if you have a set which is of the form A comma B in I naught square. This is compact, right? This is a closed and bounded set. So by the
Okay.
Heisenberg theorem, this is compact. But this L cannot be written as such a closed interval, right? So, but it still doesn't say whether this is compact or not. So, what do you think? Is it compact? So, what do we know about closed subsets of a compact?
Yes, it's closed subset of compact is compact.
Right. So, this means that L is compact. So, the answer is yes. So we see that we have to use the properties and theorems that we have proved. So they are there for a purpose, and we use them to deduce many things. Once we are given a new object, we try to determine what are its properties using those lemmas and theorems and corollaries, all this list of different results that we have seen before, right? So yeah, so this is just a detour of ordered topology and the ordered square. I hope things are clearer now, Mr. Kalimutu.
Thank you, Professor.
Yeah, it's fast. I'm sorry, this is the I have to go very fast, but you can watch the video again, and this will be uploaded on the website. You can watch the video again and play it back to go slowly. Okay.
Okay.
Yeah. Let me see any other questions. Connectedness. We have already seen that this is connected, right? I naught square is connected because it's a linear continuum, so it's also connected. Okay, let me add this here. So this is again a theorem. I naught square is connected as it is a linear continuum, and we know that any interval or any ray, in fact, in a linear continuum is any interval, let's say AB or a ray A plus infinity or minus infinity B. So this is, by the way, these are the sets that you defined as x in I naught square, such that A is less than x. Similarly, this is defined as x in I naught square, such that B is x is less than B. Right? So any interval or ray, by a ray I mean these kinds of sets, these are connected in a linear continuum. Right? So I naught square is connected. We have also seen that, so let me put this as 1. So I naught square is not path connected. Right? So I think I proved this in one of the lectures that it's not path connected, and the problem there was the intermediate value theorem was used to show that if you have any path between any 2 points, let's say here. So let's take a point here and let's take a point here. Then any path that has to go like this must fill out the whole thing. Okay, so it actually has to fill out the whole thing, and this causes problems with the countability and so on. So so the only path connected components are just these vertical lines. So the vertical lines like this, these are path connected. Of course, you can go from one point here on this. Any 2 points can be connected by just a straight line like this, but these are the only possibilities. So If you add any point other than this vertical line, then it will not be path connected. So there are infinite, in fact, uncountably many infinite path connected components given by each vertical line at each point in the x-axis. So it's not path connected. So these are the both connected and connectedness properties. What about limit points? Well, limit points again, because it is compact, it is a limit point compact. Okay, so every infinite set has a limit point. So let me again. This is also something we proved. So I0 square is limit point compact, which means that every infinite set in I0 square has a limit point. Right? So of course, limit point compactness is a very nice property. Even though it is not a metric space, it's still it's a limit point compact. And finding limit points is pretty easy. I mean, you just you have to see that the topology on the vertical, each vertical segment is the same as the topology on R. Okay, so it's a homeomorphic to an interval in R, and using that you can find limit points quite easily. So yeah, I think I covered all of your points. Any other questions you have? I can ask you. Or any other questions outside this ordered square business?
Yeah, this is clear, Professor.
Thank you. Yeah, I hope.
Thank you.
Yeah, so the point is to use all the, so because of time constraints, of course, it's not possible to go into detailed applications of all the theorems I'm proving. But so this is something I wanted to say, is that why do we look at the proof of theorems? Because I sometimes hear from students that, you know, it's not necessary to look at the detailed proofs of the theorems that we're using. We just need to know how to apply them to solve a problem. And that's correct. Of course, you need to know how to apply them to a particular problem. But when you are looking at a proof and you're going through a new idea, so usually, for example, the proof of Tikhonov theorem, the proof of the Bayer category theorem, or even Urizon's lemma, Thiel's acceleration theorem, all these big theorems, there is some new idea involved, right? So these are all deep theorems, and when you're going through the proof, you are trying to follow a new idea, and that already creates this is a mathematical training that you want to have, is that how to think abstractly, how to reason abstractly, how to follow the logic, how to create your own logic in a proof, and so on. So knowing the proof, when you are looking at a problem, you might as well think of, okay, I think I have seen this kind of an idea in a proof somewhere, and that is used there. So of course, it's not completely necessary that you know all the details of the proof in order to solve a problem using some particular theorem, but then you're missing out on some the abstract richness and the beauty of the whole thing. So that's why I emphasize, I mean, I tell all my students, yes, learn how to apply them to problems, but also you must know, at least once you must have seen the proof and understood it properly. By the way, if you're just following someone, someone is giving a lecture and you're trying to just follow a proof, then that's easy. So what's difficult is to try to redo it. So I encourage my students to redo the proof. Once they have understood it, try to write it down yourself. And that you will immediately see that it's not easy. So that's the gold test, whether you've understood something very well or not, is that whether you can do it yourself. And so when you are looking at a proof, you think you have understood it, but when when you're starting to write out the details, then you immediately get stuck and you see that there are gaps in your understanding, and then you go back to the proof and then you try to understand what you're missing and fill out the gaps basically. So this process is important for mathematical maturity to come in a student of mathematics. And I always encourage to look at the proofs because they are usually very beautiful, very nice. The ideas are new and complex and sophisticated enough that they warrant our attention. And so, yeah, so that's my advice for all students to learn about the proofs, not just the theorems and how to apply them for a particular problem. I try to give as many problems as I can in our limited space in the assignments, but of course, I know it's not enough. So in a course like this, where there is very limited, personal interaction, it's up to the learner to kind of have this self-motivation to go through everything that's required, not just follow the lectures, but also do the assignments. When we publish the solutions, try to go through the solutions in detail, because we write the proofs in detail and try to understand what's going on. So that part is on the learners. So that effort has to be put. Otherwise, you will always have gaps in your understanding. Yeah. Okay. Are there any more questions? Okay, if not, I'll just stop sharing. If you have any more questions, you can ask me. Don't be shy or afraid. There are no wrong questions. Right? This is something also that needs. Many students feel they might ask the wrong question or something easy, but it's never no question is not worthy of answering. So the more you ask questions, the more you learn. It's as simple as that. Yeah. So always ask questions. Bother the instructor as much as you can. But it's in the end, it's you who gain from that process. And when you ask more and more questions, your understanding of your subject becomes better and better. And of course, there will be some questions which are too easy that you missed and it could be trivial or obvious. But then, this is part of the learning process, and everybody has to go through it. So, yeah. No more questions? Okay. So then I think we can stop here. Thank you for coming to the live session. And if you think you still have questions, there is always the discussion forum, and you can write to me whenever you like. Even up to the exam date, you can write to me. I'll answer.
Sure, Professor. Sure.
Yeah.
Sir.
Yeah. Any question? Okay. Okay. So I take your leave now. So thanks, and have a nice day. Yeah. Bye.
Thank you, sir.
Bye.
Thank you so much, sir.
Yeah. Thanks. Bye.